Okay, so we're going to be looking at section 2.4. We're kind of skipping around in chapter 2 a little bit. So just know that if you're following along in your book or your ebook, we're not going to do every single section in chapter 2. But for the next couple class days, we're going to be looking at polynomial and rational functions. This is a pretty lengthy topic, so we probably will take 1.5 class days, maybe even 2 class days. So first, let's look at polynomials. So the prefix poly, like outside of math, means many, right? If you're polytheistic, you believe in many gods. If you're a polygamist, you have many spouses, right? So polynomial functions, again, poly just means many, and they're just basically many-termed expressions. But more specifically, they are functions with x raised to a positive whole number exponent. So they are a big category of a lot of different types of functions. The only requirement is that the exponents must be positive whole numbers. Okay? So some of the things we've talked about this semester are actually polynomials as well. For instance, okay, I want you to know that that is not only a polynomial, but it's a what? We talked about this one this semester. It is a function, but more than that. What kind of function is it since it's x to the first power? It's linear, okay? So linear functions are polynomials, okay? The next one we talked about were quadratic functions. Okay, what kind of shapes do quadratic functions make when we graph them? We did this last time. Parabolas, okay? So those are also polynomials, though, because notice we have positive whole number exponents, right? The whole number exponents are 2 and 1, okay? But then we also have things like maybe a third power. Or maybe even a 10th power. I guess my point is it doesn't really matter. We have a lot of different classes of polynomials, but all of these would be considered polynomials. All right, and the thing about them is the graphs are going to look different, but polynomial graphs are smooth, continuous curves of some sort. So I'm going to say this, there's no corners or gaps in the graphs of polynomials. So polynomial graphs might look like this if they're quadratics, or they might look like this if they're higher power. Okay? But notice in both cases they're smooth, they're curvy, there's no sharp corners, and we don't skip over. Okay, they're completely continuous. There's no gaps in the graph at all. Okay, so now that we kind of know what the graphs will look like, although they will vary in number of curves and all of that, we also can talk about what type of degree a polynomial has, and the degree is just the highest exponent present. So let's say that I told you to find the degree of the following. F of x equals 3x to the 5th minus 10x plus 5. So this is definitely a polynomial because we have positive whole number exponents, right? No negative numbers, no fractions, nothing like that. And so this is a what degree? What's the highest exponent that we have here? 5, right? So we would say this is a 5th degree polynomial. So it's 5th degree because of the highest exponent, and it's a polynomial because it has only positive whole number exponents. Okay. And where the degree comes into play the degree is going to tell us at most how many x-intercepts we can have, or how many roots or zeros it has. So a polynomial has at most, so I'm going to underline that phrase. Okay, at most means it could be less, but no more than. Okay, so it has at most the same number of x-intercepts as the degree. But just know that it can be less. So what is the most number of x-intercepts that this polynomial could have then? Like, what's the most? 5, okay? But it could have less than that. Okay, so it doesn't always have exactly that many. Sometimes it does. But that's the most it can have. All right, so we're going to use degree for a couple of things. Not only can degree tell us what, or the number of x-intercepts we might be able to expect, it also can aid us in finding something called end behavior. End behavior is, kind of just read the terminology and it kind of is what it sounds like. It's basically what the graph does at the ends. Okay, in other words, at the far left and far right. Okay, end behavior is not concerned with what the graph is doing in the middle. It's only concerned with what the graph is doing at the far left and the far right. And so here are the two determiners of end behavior. The first one is degree. Okay, specifically whether the degree is even or odd. Okay, and we're going to talk about what happens when it's even versus what happens when it's odd. Okay. So, of course, since 5 is an odd number, this is an odd degree polynomial. Okay, if it was fourth power, it would be an even degree polynomial. And then the second thing that describes what the graph is going to do is something called the leading coefficient. And in case you don't know what that is the number in front of the highest exponent term. It's not always the one in front if the numbers aren't in order or if the values aren't in order. But it is the number in front of the highest exponent. Okay. But what we care about as far as the leading coefficient goes is whether it is positive or negative. So we can pretty easily determine the degree, and then we're going to decide, is it even, is it odd? And we can pretty easily also find what the leading coefficient is. Okay, and the part we care about, the leading coefficient for end behavior anyway, is whether it's positive or negative. Okay, so there are 4 distinct cases, if you will. Okay, so there are 4 possibilities for end behavior. Okay, so maybe leave a little space because we're going to label something to the left here. Okay, so leave a little space in your left-hand column. So if it is a positive leading coefficient, and an even degree, then the graph goes up in both directions. So if the highest power is something even, like 2, 4, 6, 8, something like that, and then the number in front of that highest power is a positive one, okay, then we know that the graph goes up in both directions. Okay. The second case, let's say there's a negative leading coefficient. We actually looked at this when we looked at parabolas, if you remember right. Okay. What did putting a negative number in front of the x squared do to the parabola? Instead of it going up, what did it do? It went down. Okay. So a negative leading coefficient and an even degree means the exact opposite. Instead of going up in both directions, we're going to go down in both directions. So notice we've covered both cases where we could have an even degree. Okay. So a really good rule of thumb here is if you can remember that parabolas or quadratic functions are an example of even functions, then this will probably help you remember this. Okay, so a positive number in front of the x squared, although it doesn't have to be x squared. I'm just talking about the most common even function, which is an x squared equation. But if the number in front of that highest power is positive, we go up. If it's negative, we go down. Okay, so notice both of these cover when we have an even degree. But what about when we have an odd degree? So let's go back to positive leading coefficient. And odd degree. Okay, so when the degree is odd, the graphs are going to go in different directions. So basically the graph is going to go up to the right and down to the left. Remember the handout that I gave you with the common graphs? Didn't we have one that was definitely an odd degree? Do y'all remember one of the main common graphs I wanted you to know? One of them was a cubed, right? Didn't I give you a handout on that, or am I thinking about my other class? I did. Okay. So remember the cubed went up to the right and it went down to the left, right? So that's just an example of something that's an odd degree and a positive leading coefficient. Okay, so the last and final case, and I'm going to maybe let you guess what you think is going to happen. Okay, so if you switch it to negative, what do you think is going to happen to the directions? They're going to be opposite or flip, right? So if you have a negative leading coefficient and an odd degree, instead of going up to the right, we're going to go down to the right, and vice versa on the left. Make sure my arrow's clear there, since it's kind of an important part of what I'm saying here. Well, that didn't help. Okay, so notice in both of these cases, we're talking about odd degrees. So I am going to want you to know these four possibilities, but notice that if you know, for instance, number 1, I think you can get number 2 for free because it just flips it upside down. Also, if you know number 3, then I think you get number 4 for free because, again, it just flips it upside down. Okay, so if you can remember cases 1 and 3, I think you get 2 and 4 for free. Okay, so if you can remember what positive leading coefficients look like depending on whether the degree is even or odd, then I think you can just flip it for the negative versions. Okay?
Does that say and up to the left?
Yes, it's just the worst arrow ever. I used whiteout and thinking that I would improve what my arrow looked like, and it did not. So yes, that is supposed to be an up arrow. That's a little better, but not great. Trying to write over whiteout's not always great. Okay, so we're just basically talking about kind of building blocks of what the graph is going to be. So let's kind of pause and do a few examples. So I want you to find the degree of the polynomial any x-intercepts and the y-intercept. And let's say that this is the function that I'm asking you to look at. So with this one, we could FOIL if we want to, because we're going to need to know what the highest power would be. I don't necessarily think foiling is really the way to go with this, okay? But if you prefer, you could multiply this all out, okay? But remember, degree is asking for what the highest power would be if it were simplified. So the highest power is not 2 on this one, okay? What you have to do is either actually FOIL it, okay? Or just picture what the highest power would be if you did FOIL it, okay? What would be the highest power if we did multiply this out, which I already said we really don't want to? So you would do x squared times x squared, which would actually be x to the what? X to the 4th, okay? So the highest power is actually going to be 4, okay? And if you need an explanation for that, that's because x squared times x squared will actually be x to the 4th. All right, so let's jump into finding the x-intercepts. Okay, we haven't done polynomials for finding x-intercepts, but we've done it for lines and parabolas. So how do we always find the x-intercept of any graph? So we're going to set what? Y to 0, okay? That is always how you find the x-intercepts. I don't care what kind of function I introduce to you throughout this semester, that is always going to be how we find the x-intercept. So we're going to set f of x equal to 0. And then we want to fully factor this, which it's already partially factored. That's why I didn't want to FOIL this. It's already actually, some of the work is done for us, okay? But do we maybe notice something about these two guys, okay? Yeah, so both of these, right? Both of these are a difference of 2 squares. And we talked about that the first week of class. So in other words, can we further factor this out a little bit, okay? And I think we can, right? So let's take x squared minus 1. What would x squared minus 1 factor into? It'd be x plus the square root of the second number, right? And then x minus the square root of the second number. Okay, so remember, difference of squares is a factoring special case I want you to know when you see it. Okay? What about x squared minus 9? So is 9 a perfect square? It is, right? So what squared gives you 9? 3, so it's going to be x plus 3, x minus 3. Okay, so now notice we have 4 pieces and we have it equal to 0. So what do we know about one of those pieces? One of these, for a list to be 0 when you multiply them, what has to be true about one of the things? One of them has to be 0, right? So we're going to say, okay, what about if x plus 1 was 0? Or x minus 1 was 0? Or x plus 3 was 0? Or finally, x minus 3 is 0? In other words, we're actually going to get 4 answers. Why shouldn't 4 answers surprise us? What was our degree of our polynomial? 4. So what was the most number of x-intercepts we could have? 4. Okay, and it looks like we had the max. Okay, so if you were trying to pick out what the graph of this one would be, it's going to cross the x-axis how many times? 4 times, right? So this is obviously going to be a more curvy function than a parabola is, right? It's going to hit that x-axis more a higher number of times. All right, so how do we find the y-intercept of anything at all? Set x to 0. Okay, so in other words, I need to find f of 0. So just take the original equation just as it is and plug in 0 in both places where you have an x. And then make sure you do your order of operations, right? So we would do parentheses, but within that we would do exponents first. But what's 0 squared? 0. Just 0, right? So I would end up getting -1 for the first parentheses and -9 for the second. So I end up getting 9, okay, or y equals 9. Okay, if my math lab asks you to list these as coordinate points instead, how would you list this point, for instance? How would you list y equals 9 as a point? 0, 9. And then how would you list all of these? They would be like the number, comma, 0, right? So sometimes my math lab will just want you to say x equals and y equals and then whatever the answers are, and then sometimes it might ask you to put it in point form. Okay, So let's do maybe another one that is maybe a little bit larger in degree at least. So I'm going to be lazy and say same instructions. In other words, I want you to find the degree, the x-intercepts, and the y-intercept. By the way, you can have multiple x-intercepts, but only ever one y-intercept. How come? What test would it fail if it had multiple y-intercepts? A vertical line test, and it would no longer be a function. So you're only ever going to have one y-intercept, but you have a possibility of multiple x-intercepts. Okay, so again, we definitely don't want to multiply this out. Okay, let me show you on the board what it would look like to multiply it out. I think we can all agree we wouldn't want to. So this would look like 2x plus 3, 4 of them. And then how many of the second parentheses? 5 of them. Okay, so I'm just going to say dot, 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 because I'm tired of writing that. Does anyone here want to do that much foiling or that much messing around? Like, we don't want to, right? And we don't need to. We just need to try to picture what the highest power would be if we were to do that big old mess, which we just decided we don't want to do. Okay, so in other words, we just need to figure out what is the highest power we would have. Okay, we have a 4th power times a 5th power. So what's going to be the highest power we'll have then? It's going to be 9? 9. Okay, and how come it's going to be 9? It's because it's basically something to the 4th power times something to the 5th power, which is something to the 9th power. Okay, so we don't want to actually do it. We just want to picture what would happen if we did it. Because frankly, another reason we don't want to do it is because notice it's already factored for us. So when we go to find x-intercepts, it's actually not bad at all, right? So if I set y equal to 0, a lot of the work is already pre-done for me. So this is going to be 0 equals my 2x plus 3 to the 4th, and then x minus 5 to the 5th. And since it's already factored for me, then what do I do with each parentheses? Just like I did in example 2. Set each of them equal to 0. Because one of them has to be 0 for the list to equal 0. So if you subtract 3 and divide by 2, you're going to get negative 3/2 for this one. And then you're going to get 5 for this one. Okay. By the way, how many times is it going to cross the x-axis on this one? Only how many times? Twice. But how many could it have done? It could have done it how many times? 9 times, right? But remember I said at most it would be 9 times. So in this case it's only twice. Right? But by the way, this kind of makes up for the 9 because this root occurred 4 times and this root occurred 5 times. And 4 plus 5 is 9. Okay? So essentially what can you always kind of do with the exponents in order to get the degree? You add them up. Okay, that's it. Okay, if you have your exponents, you just add them and you should be able to get the degree. All right, last but not least, let's do our y-intercept. So we want to set x equal to 0. So g of 0 is going to be 2 times 0 plus 3 parentheses to the 4th, and then 0 minus 5 parentheses to the 5th. So we're not going to try to eyeball this. This is going to be actually quite a large number because we're going to have to raise some numbers to some pretty major exponents. So let me see if I can get this sort of visible. Okay, so I'm just going to enter in just what I've got there. You don't even have to simplify it, although you could, but you can actually do, notice I'm just entering in exactly what I had here, parentheses 0 minus 5 to the 5th. Okay, so you can clean it up before you plug it in the calculator or just plug it in the calculator as it is. But it is going to be a pretty big one. Okay, so let me slide that over, but the answer is, let's see if I can make sure you guys can see it, sorry. But the answer is negative 253,125. Okay, so that would definitely be one we wouldn't want to graph, right? That would be kind of a booger to graph. Let me move that over there. So if I asked you to, what would be the point for that, even though that would be a really weird point? how would you write that y-intercept as a point, as a coordinate point? It'd be 0, comma, that big number, okay? 0, comma, negative 253,125, okay? Okay, so that's kind of what polynomial graphs look like, okay? Just know that they're going to be kind of all different shapes. So let me show you some examples. I printed off a couple of the things kind of from the homework example. So let me just project these. You don't need to draw these. We're just kind of going over them, okay? All of these graphs that I'm showing you on screen, they're all polynomials. They're just different types of polynomials, okay? How do we know that they're all polynomials? What were the two kind of qualifications that I said all polynomial graphs will have? They'll be smooth curves, right? In other words, no sharp corners, and they'll be what? Continuous was the second requirement. In other words, there's no gaps, okay? There's no jumps or anything like that, okay? So notice, while these all are very different looking graphs, they're all different types of polynomials, okay? The only one we probably really know well is number 15, right? Or the third one down the list, right? What kind of graph is that? Definitely, because of how it looks. It's linear, right? But the rest of them are just various types of polynomials, okay? So just a couple of things. What do we notice about this one? It goes up from on the left and the right, correct? So what kind of power do we know that it's going to have as far as, we know it's going to be an even power, right? Because it goes up from left to right, okay? So it's going to be some even number power, okay? And then, by the way, how many times does it cross the x-axis? Twice, okay? So if you had to say what the possibilities for the degree here were, you wouldn't say 2. How come? Even though it only crosses twice, there's a name for 2 x-intercept type equations, right? What are those called? What kind of shape only crosses twice? Parabolas, right? Or x squared equations. So this is not an x squared equation. So that means what would actually probably be the power then? Instead of 2, it would be what? 4. And why did we skip over 3? Because then that would have been an odd degree, right? We know it's even degrees based on what it does at the ends. Okay? So you're going to be asked on the homework to answer questions based on, what's the degree, what's the x-intercept, what's the y-intercept, but then you also might get a graph given to you, and you might have to explain why do you think that looks like a polynomial. In other words, it's smooth and curvy, and it's continuous, and then what do you think the degree might be, okay, based on whether it goes up and down and all that good stuff, okay. What about this one? Notice it goes up to the left and down to the right, correct? Okay. So what kind of degree do we know for sure that this is? As far as even or odd. We know it's odd, right? So think of the odd numbers we know, right? Why isn't the degree going to be 1? If the degree is 1, what's it going to look like? That, okay? Degree 1 polynomials are linear, okay? So we know that this has to be at least what degree then? 3. Not 1, but it has to be 3, right? By the way, what else do you know about this graph? What do you know about the number in front of that x cubed probably? Is it negative or is it positive? It's negative. How come we know it's negative? Because if it was positive, how would the graph look instead? It would have went up to the right and down to the left. Okay, so those 4 cases that I mentioned, okay, whether the power was even or odd, and then whether the leading coefficient was positive or negative, we need to start committing those to memory. Okay, so, but your homework will let you try things multiple times, so I think, like, the structure of the homework will be good for stuff like this. It'll allow you to practice different kinds of graphs. Okay, so that's polynomial graphs. So I want to also at least start talking about rational graphs. We won't be able to finish it, but that's okay. So we have polynomial graphs that are positive whole number type equations, and the graphs are curvy. But we have a second class of function called a rational function, okay? The word rational means fraction. So I like to say they're fractional functions. But basically what they are is they're the quotient of 2 polynomials. What does the word quotient mean? What operation? Division? Okay, and that's all a fraction is just a division. So here is an example, or maybe more than one, of a rational function. 1 over x plus 3 is rational, but so is x squared minus 3 over x plus 4. So anytime you have a fractional function, basically where x is in the denominator, it's going to be rational. Okay, and the graphs to these are usually curved. And they're usually not continuous. Okay, in other words, there's usually some gaps or some jumps or some breaks or something like that. All right, so just like we broke down the pieces for a polynomial graph, let's break down some unique pieces that rational functions have. So the first thing is these graphs are going to have what we call asymptotes. So the first type of asymptote is a vertical asymptote. I'm going to abbreviate that VA because that's a long word to write out. That's a long phrase. Okay, so vertical asymptotes are basically not really part of the graph. They're boundary lines for the graph. So it's a boundary line that the graph approaches but doesn't cross. What I mean by approaches is it gets super, super close, but it doesn't actually touch or cross it. So let me visually show you what a vertical asymptote is, and then we're going to talk about how to find it. So let's take maybe the first example that I gave you up there. So let's say I want to graph 1 over x plus 3. Let me get it out of the glare. First thing is, notice when I put it in parentheses, what am I putting around the denominator? I think I just said parentheses, but anyway, when I put it in the calculator, what do I put around the denominator? Parentheses, right? So anything with more than one part, stick a parentheses around it. That'll make your life with the calculators much, much easier, okay? So let's go ahead and graph it and pay attention to what it looks like, right? It's curvy, right? But would you say that's continuous? No, like you wouldn't be able to draw that with one swoop of your pencil, right? You would have to lift your pencil to draw the second piece. So it is not continuous for sure, okay? And actually, doesn't it look like it has a vertical boundary line? Okay. In other words, doesn't it look like there's a vertical line that it's getting super close to without actually crossing? So where do you think it looks like it is if you kind of squint and see? It looks like at -3, there's a vertical boundary line that it's staying away from, right? But just like a little kid, when you tell them not to do something, it's going to get as close as it can without actually crossing that line. Okay, so that's what I mean by approaching. It scoots super, super, super close to it. It just doesn't actually make the crossover. Okay. Okay, so that's kind of what a vertical asymptote will look like. Oh, one more thing. This is a TI-84 calculator. If you have an 83, which is just the solid black ones, does anybody have one of those that they'd be willing to let me use for a minute? Do you have it? So the calculators, even if they're TIs, they do this a little differently. So I want to show you because a lot of you I know will have this calculator at home, and I'm not dogging on your calculator. Oh, this one's dead. Does anyone have one that maybe has batteries that looks like this? The black ones? No? I should have brought one, but I didn't think of it. All right, so I'll just talk about it. So if you use a calculator like this, it's going to show the vertical asymptote as a solid line. Okay, so thank you, sorry about that. So I'm going to just sketch how the black calculators, the 83s, actually would sketch this. They're going to make it look like this instead. It's going to have the piece here, just like mine does. And it's going to have the piece here. but then it's also going to solid draw a line there. Okay, why might that be misleading if you see that? Is the line really part of the graph? It's not, right? It's a boundary line that the graph's not supposed to cross over, okay? So if you have the 83 calculators, just know that that vertical line is not actually part of the graph. They actually, it's a, in my opinion, a glitch, and they fixed it by the time they got to 84s. Okay, so there's very little differences between the calculators that you might be using at home, but just know that the 83 has a couple little glitches that if you're just aware of them, you can use it just fine. Okay, so how do we find the vertical asymptote when we don't have a picture to look at? The vertical asymptote is any x value that makes the denominator 0 once you've simplified the fraction. So notice in algebra we learned a long time ago that what are we not allowed to have in the bottom? 0. So I'm going to say once the rational function has been simplified. So 0 on the bottom is not allowed. And so anything that makes 0 on the bottom is going to be our boundary line. It's going to be the line that is off limits, but the graph is going to push the limits of what that might be. Okay, so let's do a quick example, and let's use the one that we just showed, right? So what if I told you to find the vertical asymptote of the function that we were just looking at on the calculator, 1 over x plus 3? You already eyeballed it and told me where you thought it was anyway, right? Where did we think it was? Do you remember? So let me put it back up there. So we thought that it was at what? -3, okay? And it turns out that it is, and how come if we look at the equation? What is going to be the off-limits value for x anyway? At -3, right? So to find the vertical asymptote, first we simplify. Notice there's nothing to simplify here, right? There's nothing that could be canceled out. So we're going to set the denominator equal to 0, and so we're going to get x equals -3, okay? When you type or write the vertical asymptote, make sure that you write x equals -3, because it's not just the number -3, it's the vertical line equation, x equals -3, okay? And remember, vertical line equations from our linear section look like x equals and then a number, okay? So I know it might seem nitpicky, but I want to see x equals and then whatever that number is, okay? Okay, so last one of the day, and then we'll pick back up with this on Friday. So find the vertical asymptote of g of x equals x squared minus x minus 6 over x squared minus 4. And let me finish my sentence up here. I got ahead of myself. I'm going to say once it has been simplified. So add once it has been, so it's actually a real sentence. Otherwise it's, oh no, never mind. I said once before. Just kidding. Okay. Maybe I should read all of it. Yeah, once the rational function has been simplified, that makes total sense. I was doubting myself. Okay, so we look at this one and we think, I bet that's not fully simplified. Okay, so here's where you have to pull out your factoring skills. So we're going to start with what I think will be easier for us. Let's start with the bottom. We've already dealt with this today. What kind of factoring is this? It's a difference of what? Difference of squares. So this is going to factor into x plus 2, x minus 2. That's a factoring problem that I want you to just know right off the bat. Okay? And then what about for the top? We don't need AC method, because the coefficient in front of x squared is not anything other than 1, right? It's just 1. So what are the factors of -6 that would add up to -1? -3 and +2, okay? If you need to spend some time factoring, then do that, okay? I'm just telling you what the factorization would be, and you need to get to the point where you can factor quickly and efficiently. So why did I factor these out? What do you notice now if I'm wanting to simplify? We can get rid of the x plus 2, okay? And so actually we only have one vertical asymptote, right? Now we can set the denominator equal to 0. So we have one vertical asymptote at 2. Okay, so what does that mean about our graph? It's going to get really close to the line at 2, but what's it not going to do? It's not going to cross over it or touch it. Okay, so just make sure that we simplify first. So let's underline simplified so we remember to do that. Okay, so just quick reminders. You have a homework assignment due today. What else is due today that we talked about at the beginning of the class? The first attempt to your comp exam with your work and honesty statement uploaded with it as well. Okay, all of that is due tonight. Okay, I might send out an email reminding you, but let this announcement serve as your reminder too. Okay, if you came in after roll call, come see me.